Hey, good day, good people. Let us look at strain energy. All right, let us look at strain energy. All right. When a force is applied to a member, its length will change, either lengthen or shorten. Now, this is what they mean. When the force it's been applied on this member here, right? What's going to happen? You'd realize that it will lengthen if we are applying what? If we are applying the force tensile. Then if we are applying the compressive, it will obviously shorten. It will obviously shorten. Right. That is the first indication that we are getting when we are applying a force to a member or in any steel structure. Then let us therefore define the strain energy. Strain energy is defined as the energy stored in a body due to transformation. Now, the definition says it's an energy stored in a body due to what? To transformation. Meaning, when you apply the force and there's a transformation here, as you can tell, there's a change in length. Now, there would be an energy stored due to what? To transformation, right? That's what we are basically looking at, or that's what we will be dealing with on this topic. Now, let us look at when the energy is applied, what's happening, and so forth. And work is done because the force applied moves through the distance x. Now, the distance x would be this distance here, from here to there, from point A to point B. Then we are saying the work is done. Then that's where this definition comes in. It's a energy stored in a body due to transformation. From point A to point B, there's a transformation and there's a stored energy. Remember, energy cannot be created or destroyed, but it can only be transformed. It can only be transferred. If that's the case, we say that the energy applied to the rod is absorbed by the rod, and when the applied load is removed, then the energy is released by the rod. Now, from this point, this is what we are saying, okay? The energy will be stored, as I've explained, due to what? To transformation. Now, when you remove the force, right, the energy would be released in the rod, meaning this material can then go back to its shape and size, meaning this strain energy, it occurs within Hooke's law. Within Hooke's law, whereby a limit of proportionality is not exceeded, whereby limit of proportionality, it's not exceeded. Is not exceeded. It means a strain energy is applicable where? Under Hooke's law. It is applicable where Hooke's law is. Strain energy. This is where strain energy is applicable, because beyond this point, there's transformation. That is why when you release or remove the force, you are releasing what? The energy. Then this material will go back to its shape and size. Therefore, work applied to the rod equals to strain energy. Please make note of this point as well. Work applied to the rod equals to what? To energy. By the way, we know that work done equals to force multiplied by distance. The SI unit, it is joules. Energy. The SI unit for energy is what? It is joules. This is exactly what they are saying to us here. All right. There are three methods of load application. All right. There are three methods that we can apply in causing this material to stretch from point A to point B. Right. There are three methods that we can apply of in any material. We are having gradually applied load. We can apply load gradually, or we can suddenly apply the load. or we can apply the shock load. Now the shock load, it is more of the shock absorber. Like in your car, you are having those springs and they are having the shocks inside. They absorb the shock as a result of what? Of the, let's say you are driving your car and there's a hump. Now because of it is a hill like, when the car climbed that hill, when coming back to the flat surface, it will absorb that shock. That's what we'll be basically looking at under your shock load, right? Then let us then examine or rather the application of gradually applied load. Under gradually applied load, you are applying the load gradually, as in like slowly. Let's say here's the material here, right? You are applying the force tensile. Now you can tell that this force, you are applying it gradually. Hence the transformation would be what? Would be gradually as well. Now if that's the case, force equals to W. The W, it is for weight, okay? W, it is for what? For weight of what? Of your beam. You apply the force gradually, so now F equals to what? To W. Now this is the formula that we will be working with under the gradually applied load. Hence, they are saying the force that you will apply, it is equal to the load. Remember W, it is mg, right? To the load, mass to the load. But you are applying it gradually so. Right, now in calculating the strain energy under the gradual load, it will be 1/2 force multiplied by x, right? Gradually, that gives you the picture that under gradually you are actually applying the average energy, load or force. Hence the formula, it is half F multiplied by X. Now X, we know that it is FL over AE. It is the change. X, it is the change in length. It is the change in length. Now if that's the case, if this is the formula of calculating the gradually load, then we will have F squared L over 2AE. Why 2AE? Remember, you are having FL under the change. Then it will be multiplied by 1/2 multiplied by what? By F. F multiplied by F, it gives us F squared. Then it will be F squared multiplied by L divided by what? By 2AE. Now this is the formula that we will be using in calculating the gradual, if the gradual load it is applied. Now this is the formula that we'll be using in calculating what? The strain energy. This would be the symbol for strain energy, the U. This is the symbol for strain energy. This is the formula that we will be applying. If we unpack the formula, this is the formula that we will be using under the gradually applied. And please don't forget that under gradually applied, F equals to what? To W. Okay. Now, if you are given compounded material under the gradually applied load, you are given this compounded material. If force tensile, it's been applied, or compression, it doesn't matter. You are having unit 1, you are having unit 2, you are having length 1, you are having length 2. How do we calculate the strain energy in one member? We said it that it is this formula in calculating the strain energy under one member. This is the formula. Okay. Now, if you are having compounded, that means now you are having U1 plus U2, right? Then in calculating the total strains, the fact that they are connected in series, this is the formula that you will be using in calculating the total strain. Now, under gradually applied load, that means you are having UT equals to F2L over 2AE plus F squared L over 2AE. Now, if it is of same material, then the E would be the same. right? If the length, they are the same, then it will be length equals to length. But if they are not the same, if the length it is not the same, then you are having length 1, length 2. If the young modulus, they are not the same, then you'll have E1 and E2. But if they are of the same material, then this it is applicable. If you are given E as 200 gigapascal, that means for unit 1 you'll have 200 gigapascal, unit 2 you'll have 200 gigapascal, all right? Then for force, it is common. The force that it is applied there, it is common. But what is it that we know about force here? We know that force, let's say you are not given force. We know that force, it is calculated from the smallest area, as much as stress, it is calculated from the smallest area. It means you in calculating force, you will need stress equals to force over area and calculate what force. If force it is not given and you are given what stress, it means the stress that will occur on the smallest area, it is max. Then you can then calculate force and use this force in this formula to calculate what total strain energy. Now, if given compounded material like this, don't forget as well how to calculate the change in length. This is the formula that we know in calculating what the change in length. Xt equals to FL over AE plus FL over AE. Right. Why we are using the same formula in calculating the strain as calculating the change in length? Remember the definition of strain, right? Remember the definition of strain is defined as energy stored in a body due to what? To transformation. And what is transformation? Transformation, it is the change. Transformation, it is the change. It can either be shortened or lengthened, as we defined here. When a force is applied to a member, its length will change. Its length will change. Now, the fact that the strain energy is the energy stored in the transformation. Hence, we are using this formula of strain. Hence, we are using this formula to calculate what? To calculate strain. Hence, we are using this formula to calculate the strain, good people. That is why they are similar, okay? But that which makes them not to be the same, it is the application of the force. F equals to W. It is the application of what? Of the force. That is why under your strain energy, you are having F squared. But under the change, it is only F, okay? Right. Then we have that which we call the proof of resilience. Is the greatest amount of strain energy. Now, when you look at the definition, it says it is the greatest amount of strain energy which a member can absorb without suffering permanent distortion. It means this member can absorb too much energy without suffering the permanent deformation. Why? Because the whole deformation or energy, it has to be within the Hooke's law. That when you remove the force, the material has to go back to its shape and size, meaning the energy has to be released. Now, this thing I found with the electric concept, whereby capacity has to be discharged. When you discharge the capacity, you are releasing electrons stored in the capacity. Now, if the electrons are not discharged on the capacity, when you touch the capacity, then the electrons will be released on you, then you will be electrocuted, okay? Now, just imagine you are applying the torsion force, okay, on this material. You are applying the twisting force, yeah? You are applying the twisting force. Then you remove the force here. Then this material gets to be, yeah? Then you get to have a bit of of the turning force stored in that material. Ne? Then when you come tomorrow and touch or take hold of this rod, then the rod discharges itself on you. Boom, it gets to be strengthened. You can imagine what is it going to do to you. It's going to break your hand or it's going to hurt you. Now, this, it is not applicable. It's not the case with what? With the steel. I'm just giving you the picture. It's not. That is why immediately when you remove the force, the material goes back to its shape and size. Immediately it goes back to its shape and style and size, I mean to say. No, it's not like electricity, the capacitor whereby it stores energy. Yeah? Now, in calculating the proof of resilience, this is the formula that you will be using. I've denoted it as PR equals to stress over 2 multiplied by E multiplied by area multiplied by the length of the rod or member or steel. Yeah? This is the formula that you will be using in calculating what? The proof resilience. Then in calculating the modulus of resilience. Now the modulus of resilience, it is made up of what? Of proof of resilience. Now I've denoted the modulus of resilience as MR. Now in calculating the modulus of resilience, it will be a stress divided by 2 multiplied by Young modulus, okay? Then the SI unit here, hence it will be Pascal per cube. Right, the SI unit, it will be Pascal per cube, okay? This is the formula that we'll be using for modulus of resilience. Now, strain energy, it's not much of the problem. Hence, I only dealt with a few notes in giving you the picture of what's happening under the strain energy, that which we need to know, right? That you need energy. For instance, let's give you another example. You need energy to pick up a box lying on the ground. You need what? Energy. But you can tell, now check this. When you pick up this box on the ground, yeah, we will apply the suddenly applied load. Meaning here you are having either F equals to, it is 2W, it is 2F equals to W. Meaning you need to apply twice the force in picking up what? The box that you don't even know it weighs how much. If the box it weighs 10 kgs or 5 kgs, you need to apply twice the force for you to do what? To be able to pick up this box from the ground level and to a certain height to the height of your waist. You will need to pick up it, with twice the effort. Yeah? That's what we will be looking at under the suddenly applied load. But under gradually, these are the formulas that we'll be working with under the gradually. This is the formula that we'll be working with. We'll do the application later on under the gradually and suddenly. But now, let us look at the suddenly applied. We'll look at the suddenly applied now. Thank you, good people.